Hi, my name's Ashley, and this is my project Pinafore. So we all have information stored on our computers, stuff we've collected, stuff we've generated, and I'm thinking about kind of home use in particular, stuff like contacts and events, and pictures we've taken, videos we've taken, and that's kind of all stored on our computers. And there are two basic ways in which we store this. So one is in a type-specific application. It's like a photo manager, right? And it has a fixed schema, fixed idea of how you want to organize your stuff. Has a great user interface, but it's kind of fixed. At the other extreme, there's the spreadsheet. Kind of very loosely typed. You can mixes up types and data, but it has a pretty limited user interface. It's just just got a grid of cells and maybe some charts and things. So Pinafore is a project which attempts to bridge those two ends. It's a strongly typed language which allows you to express whatever structure you want for your information. And it'll automatically store it as triples, and it allows you to compose user interfaces for it. So that way you can organize the information the way you want, and you can present it the way you want. So let's first talk about the language. So Pinafore is a strongly typed language, and the type system is essentially Hindley-Milner extended with subtyping. So Hindley-Milner is the type system on which ML is based, on which Haskell is based. It's a very straightforward type system. So people had tried to extend Hindley-Milner with subtyping before, but generally speaking, the results weren't decidable. Stephen Dolan's algebraic subtyping, by contrast, is decidable. Every expression, if it has a type, then it has a principal type, and you can determine that type. You can infer that type. Dolan typing also includes record types, which Pinafore omits, since they're not really a good match for the way Pinafore stores information. It also has recursive types, which Pinafore omits for the time being, though I may have to implement that. Apart from that, Pinafore is written in Haskell, looks very much like Haskell, and has a number of Haskell's features, such as laziness. You can do sort of fixed point tying the knot sort of things, pattern matching with case statements, separation of pure functions from effects. So what is a subtype? So it's a relationship between two types. We say P is a subtype of Q. It just means every P is a Q. Or alternatively, allow a P where a Q is expected. And of course, if you're familiar with any of those class-based languages like Java or C++, then you already know about subtyping, right? Every derived class is a subtype of its base class. So for every subtype relationship, there's an implied function from P to Q. Now, in Dolan typing, this function does not have to be injective. You don't necessarily have to be able to go backwards from Q to maybe P. And in Pinafore, most of the subtype relationships are not injective. You can lose information there. So Dolan typing distinguishes positive and negative types. So if you're not familiar with that, positive types are the types of values, and negative types are the types of expectations of values, such as function arguments. And most types, such as of integer and text and so forth, can be either positive or negative. And type checking, in Pinafore, it's almost always of the form, does this positive type fit inside this negative type? So for Hindley-Milner, when you're doing type checking, you have two type expressions with variables, and you try and substitute in the variables until they match. Whereas in Dolan typing, you have a positive type and a negative type, and you substitute in the type variables until the positive type is a subtype of the negative type. So it sort of fits in there. So Pinafore has type constructors similar to Haskell, such as maybe or list, or the function type constructor. But there's a key difference, there's a key restriction. all type parameters to type constructors are of kind start as ordinary types. And furthermore, each parameter must be either covariant or contravariant. So covariance is just if A is a subtype of B, then FA is a subtype of FB. We say F is covariant or F is covariant in its argument. Contravariance is the opposite. If A is a subtype of B, then FB is a subtype of FA. So covariance respects the subtype relationship, whereas contravariance inverts it. So this is actually kind of awkward, right? Because naturally there are many type constructors we'd like to use which aren't naturally covariant or contravariant. So for example, if you think of something like a ref cell, where it can just store information and you can write to it and you can read from it, then you'd want a type that, had the parameter of that type would be the type that was stored, right? That's not naturally covariant or contravariant. So what you do in Dolan typing and Pinafore is you use a contravariant-covariant pair. And Pinafore has a special syntax for this. So here it uses braces, minus A, that's the A here is the contravariant type, and B is the covariant type. So Dolan typing has these lattice-like type operators. So there's a negative type called any. Remember, negative types are expectations that says, I don't care, I'll accept anything there. And it has, if you have two negative types, P and Q, then P and Q is a negative type. And dually, there's a positive type called none, and P or Q is a positive type. So P or Q means this thing might be a P or it might be a Q, but I'm not telling you which. So this is different from an either PQ, right? So either PQ, it actually tells you it's either left P or it's right Q. But P or Q is just, you don't know what it is, it's a P or a Q, you don't know. And really the only thing you can do with that is if there's a common supertype R. So if P is a subtype of R and Q is a subtype of R, then whatever you've got, P or Q, it's a subtype of R. Dually, P and Q means you're expecting something that must be a P and it must be a Q. So if you have a subtype, a common subtype of P and Q, then if R is a subtype of P, R is a subtype of Q, then whatever it is, it's a subtype of both P and Q. So here are a couple of expressions in Pinafore where these types show up. So in the first case, so we have a function, it's bound to B, and then it's passed as the test of this if-then-else expression. So obviously B is a Boolean. And then if we look at the two branches here, one of them's a text, and the other one's an integer. They're two completely different types, right? So in Hindley-Milner, you could not give this a type. In Dolan typing, that's not a problem. It just smashes those two types together. It's a Boolean to text or integer, right? In the second case, we have this function. It's x is the arguments here, and we pass it to the integer addition function, first of all. So it must be an integer. And we pass it to the text length function. So it must be text as well. So in this case, we have a function from integer and text to integer. So that second case is probably a type error. And this is a thing about this type system, is that your type errors tend to get deferred a bit. When we come to actually use this expression, you probably find that it didn't work the way you expected. It will probably generate a type error a bit later. So generally speaking, Dolan typing is more likely to be able to give types to things, and then a bit later you discover your type error. Okay, so now I'd like to talk about the way Pinafore stores information. So it basically stores it in a big soup, which is just a SQLite 3 database in your home directory. And this database has two tables. One of them is the triple table, which stores assertions in sort of predicate, subject, object form, where predicate and subject are the primary key. And all those columns are 128-bit UIDs. And that has a literal table for actually looking up Booleans and numbers and so forth by their hash. And so the hash column of the UID will tend to match up with the subject and object columns of the triple tables. And I'll give a couple of examples. Pinafore erases types. It does not store information about the structure of types, nor does it store information about what values have what types. They're completely erased. So here's an example. The name of P is James. So P is going to be some value of type person, say. And that person is basically a wrapper around a UID. So here it's stored as one row in the triple table, name, P, and then the object is a hash of that string James. And one row in the literal table so that we can look up that hash back to that text. And the name will be some property which is specified in the Pinafore script together with its UID. So here's a slightly simpler example. The mother of P is Q. So in this case, it's just one row in the triple table. P and Q are both values of type person. Mother is a property, which becomes a predicate in the table. And then P is the subject and Q is the object. So here's the actual Pinafore that will write those two assertions into storage. So this is one expression, and it's a let expression. It has the form let declarations in expression. And that latter expression is a do block, a do expression. So Pinafore is roughly based on Haskell, but it does not have layout. Instead, it uses semicolons to separate lines, separate declarations, and separate lines in the do block. And do blocks are terminated with this end keyword. So I've put the keywords in blue and the anchors in green. And the anchors are the things that get hashed to generate UIDs. So let's focus in on the declarations. So this is the same, but now I've added in the type signatures. So Pinafore will infer type signatures if you don't put them in. But here I've put them in to make it a bit readable. So first of all, person is an open entity type. So an open entity type is a type which we can just generate new values of using there's a new entity function. We'll just generate new values of that type. And we can also statically declare values of that type using the entity keyword, which we've done twice at the bottom here. So here we've bound P to entity person, and then this anchor here in green. So an anchor is an exclamation point followed by a UID or followed by a string which gets hashed into a UID. So each open entity type is a wrapper around 128-bit UID. So here that's the value that it uses. And again, we do the same thing with Q. And we also declare two properties. So the idea is the name of a person is text. So we declare that property from person type to the text type. And then we also declare an anchor, and that's the UID that will be used in the predicate field in the triple table. And of course, the mother of a person is a person, so we declare a property from person to person. So name and mother have morphism types. So properties generate morphisms, and morphisms, as the name suggests, can be composed, and there's an identity morphism for each entity type. Okay, so now let's look at one of the lines which writes an assertion into storage. So we start off with P is of type person. Now the first thing we have to do is lift that to a reference type. And there's a special syntax in braces that will lift a value up to a reference type. So a reference is a thing that can be, you can set it and you can get it. But when we use this braces notation, you can't, the references it creates are not settable. If you try to set it, it will sort of throw a little exception. So this reference type, now a reference type, because it's a sort of gettable, settable thing, it's not naturally covariant or contravariant, so we have to use this pair of type parameters. Contravariant type is any. We can attempt to set it to anything, and then it'll give it a runtime exception because it's immutable. And when we get it, then we use the covariant type, and that's of type person. And indeed, this syntax can be abbreviated in this case, right? We can just say ref plus person to say that that's just the covariant type. Name is it's a property, so it has a morphism type from person to text, but both ends of that morphism type are contravariant covariant pairs. So if we spell it out, then it's minus person plus person to minus text plus text. So then we use the exclamation point dollar operator to apply a morphism to a reference to get another reference. In this case, we get a reference to text. So it's both gettable text and settable text. And then finally, we apply the colon equals operator to an actual piece of text. And that gives us an action, which is essentially the same as the IO type in Haskell. Okay, so generally speaking, this reference type, as I said, ref A, but more generally, it's a contravariant covariant pair. Generally speaking, anything in Pinafore can be unknown, or anything in storage might be unknown. So this reference could be unknown. And if we attempt to get a reference that's unknown, it's going to give us an exception. We can catch that exception, that's not a problem. So references have get, set, and delete operations. So delete tries to remove the information to make it unknown. But they can also signal updates. So when we're building user interfaces attach to references. And when the reference changes in some way, then it'll signal an update to any user interface that's attached to it. And we have, as I mentioned, there's this special braces ref syntax for composing references. So in this case, P and Q are references to integer. And then this reference will it'll get the values of P and Q and add them and subtract 3. And whenever P and Q get changed, whenever P or Q update, then this entire reference that we've constructed will also update. So any user interface that's watching this reference, it might just be like a text label or something, it will spontaneously change whenever P or Q gets changed. So this is the morphism type. It's used for, so it's essentially used for expressing properties and for composing them. We have an operator for applying a morphism to a reference, to get a reference. We can also inverse apply a morphism to a reference to get a set of all the things that apply to that value. So in this case here, we're inverse applying name to a reference we've created of James. So that's the set of everyone named James. And there are also operators for applying morphisms to sets. And there's some other ways of, other sort of clever ways of combining morphisms. Okay, so there's also the set type. So this is, if we want to look at the name of everyone named James, we're going to get one of these set refs. And set refs, certain user interfaces take set refs. And so they have that same property of when the set ref gets updated, then the user interface that's watching this will also get updated. It has sort of set-like operations. You can test memberships, get all members, add to, remove from, union, intersection. There's Cartesian sum, Cartesian product, this sort of thing. So user interfaces represent user interfaces. Some of which are sort of little things like checkboxes or text labels. Others are more complicated structures, such as a table with a list of rows and different columns representing different properties. Some of these more complicated user interfaces have the concept of a selection. So in this case, you've got your table, and you click on a row, then that row is selected, and you might want to do operations on the row you selected. So that parameter will be the type of the selection. So user interface is attached to references. If you're familiar with model view controller, then the reference is the model, and the UI is the view and the controller. There's this sort of two-way communication between the two. So for example, you might have a sort of a simple Boolean reference. If you have two checkboxes attached to that reference, if you click on one of the user interfaces, it'll send a set message to the reference, which will then send an update message to the other user interface to keep those two user interfaces in sync. And you can compose user interfaces, in various ways by laying them out vertically or horizontally, or on tabbed pages, or all those other sort of GTK type things. Okay, so entities is the type of things that can actually be just straightforwardly stored in storage. So there's a type called entity, and there are a bunch of types that are subtypes of entities. There are literals, there are open entity types, which we've seen, and there's closed entity types. So literals are just things that can be represented as a short piece of text, such as text or integer or Boolean. There's some date and time, sort of like time and duration kind of types. And all of those things will end up in the literal table in storage. So open entity types, declare them with open type. You can declare a value statically with entity keyword. You can generate values with new entity, which is a function, not a keyword. And you can also declare subtype relationships with the subtype keyword. You can say subtype P is less than or equal to Q. And that will make, if P and Q are both open entity types, that will make P a subtype of Q. And if you want to declare a cycle of subtypes, that's fine. It'll just make all those types equivalent. So closed entity types resemble Haskell algebraic data types, similar to data. Each one is a list of 0 or more constructors, and each constructor has a list of 0 or more entity types. So here's an example. We want to talk about, supposing we're doing some sort of astronomy thing, and we want to talk about location in the sky. And there are two different ways we might refer to that. We might use equatorial coordinates, sort of right ascension, declination, or whatever, or ecliptic coordinates. So we create two constructors. And as you can see, if you're familiar with Haskell, it's very similar to a Haskell data type. The only difference is we have to add an anchor for each constructor. And this anchor will determine how to store this sort of thing in storage. And what it'll do, so for example, if we have ecliptic lock 5 and 7, first it will store 5 and 7 in storage using the literal table, and then it'll hash that entire thing, and that creates the UID that it uses to represent this entity. And then it'll create special predicates from that UID, special entries in the triple table from that UID to those two fields, 5 and 7. So it can recover that. So this is the hierarchy of entity types. On the left, we've got literal types. And as you can see, there's a sort of numerical hierarchy here. Every integer is a rational. Every rational is a number. There's some date and time types. In the middle, we've got open entity types. And there's a special type called new entity, which is a subtype of all open entity types. And on the right, we've got closed entity types. And also, these special types are also essentially closed entity types. There's the maybe and list pair in either type constructors. If their arguments are subtypes of entity, that makes them entity types as well. So, for example, if we have there's an open entity type called person, then list of person will also be an entity type. So we can also put lists of persons into storage.
It looks like you've got a recursive type there, but you said I don't have recursive type, so either entity. Is that's a subtype of entity?
Yes, it is.
That looks recursive to me. But maybe I'm just
It is, yes, and that's why I'm going to have to implement recursive types eventually if I want to fix that. Yeah, yeah. In fact, all of these. So it does cause problems. I mean, it doesn't. The type system is still sound without recursive types, but it is a bit of a corner case. Okay, so Pinafore is robust with regards to what it finds in storage. So if something is missing that it expects, that's no problem. It's just unknown. If there's a literal that doesn't parse, that's fine. It's just unknown. So this means there's quite a lot of changes you can make to the to your schema, to your type system. I mean, to the way you've defined your types in the script. There's quite a lot of changes you can make without actually touching storage. So obviously you can add or remove properties. If you add new properties, then initially all the values of those properties will be unknown. And if you remove a property, that's fine. The information's still in storage, you're just ignoring it. You can also add or remove constructors to closed entity types. If you add a constructor, that's a new kind of value for that type. If you remove a constructor, then any information that used that constructor will now become unknown. And you can change open entity, you can change subtype relationships, that's fine. You can change the names of things. And all that actually matters is the anchors. The anchors are the things that actually link what you've got in your script with the way things are stored.
Do the anchors have to be distinct within your scope?
They should be. Yes, ideally. And that's one of the things I intend to implement at some point is actually a checker to make sure that you haven't duplicated any anchors in your script. Okay, so currently Pinafore's at a kind of proof of concept stage. You can go to pinafore.info. You can download it and build it. There's a lot more I want to add to it. I want to add. So right now it doesn't do file storage, so you can't actually work with sort of photos or videos yet. So I want to add that in. I'd like to have a typed way of working with external data sources, such as web services and things. That would be very useful. And right now there's I'd like a richer system of user interfaces, so you can build up more interesting structures. Okay, so that's pretty much all I've got. Thank you very much. Are there any questions?
This is very interesting talk. Thank you very much. When you sat down to write this system, what things did you say, oh, I don't want to go in that direction? What did you discard before you landed on the type system that you chose?
So with regards to the type systems...
Just the thought process which led you to building it this way versus some other way. You could have sat down and said, I'm going to do this with lenses or propagators or some other approaches. Yeah,
so what I want... So people naturally think in terms of subtypes. So I want to say that, this is a way of, organizing your information, right? So presented with that, people tend to think in terms of subtypes, right? They say, people are a kind of animal and cats are a kind of animal, this sort of thing, right? Yeah. When they're building up their stuff. So what I really wanted was a type system with subtyping. So that motivated me to look for something like that, and I came across Stephen Dolan's dissertation, which came out, I think it came out in 2016, I think. It came out a few years ago.
Is that the Pinel sub?
Yes, it is. That's sort of example language he's got, yeah.
Have you thought about type classes? Or not against that?
That's a very interesting question. So one of the problems one of the awkwardnesses here is that there's no good way of doing overloading. So for example, I actually have 3 separate addition functions, right? I have an integer addition, rational addition, and number addition, and I use 3 different symbols for them, right? So that's kind of an awkward thing to do. Probably if I wanted to solve that problem, I'd look into some kind of type classes approach. But as far as I know, there's been no, and I talked to Stephen Dolan about this, but as far as I know, there's been no particular work done on that. So.
Yeah, so just for some background, we're actually in the process of attempting to retroactively formally specify a language using the ML sub.
Oh, okay.
But we're just at the early stages of that. It'd be interesting to know if you ran into any things that perhaps weren't covered in the paper, if it was comprehensive, or if there's any sort of edge cases that you found while implementing the type system.
Yeah, so I mean, I came across, like, I guess, three main awkwardnesses. One of which I just mentioned, it's difficult to do overloading. The other one is having to do this covariant-contravariant pair. It's a little bit awkward. And there's a third case when if you create a type signature under a lambda, in certain cases that's ambiguous, and you have to detect that and give an exception or give a type error. And the other thing is I really wanted to omit recursive types because that's quite complicated. But I am, if I want to be able to say that Pinafore can always find the principal type, then I will have to implement that.
Did you have to do anything about the value restriction? Because I know in Hindley-Milner, a reference is unsound unless you have this crazy thing that ML, like standard ML, might deal with. I think you might have solved it by making the language pure. I'm not sure.
Yeah, I do the same thing Haskell does. Yeah. So yeah, the action type sort of works sort of monadically. So the same.
You mentioned schema changes for removing fields and other fields.
Yes.
Does that promote the types, or do you check is the type checking the same as schema checking over data, or what's the relationship there?
I mean, so fields are just represented as those properties, right? So if you add one, that's just a new thing, and there's nothing in it in storage yet, right? And if you remove one, you're just ignoring.
It's a single view. You don't have any translation between the storage schemas or the types.
No, not really. It's just
Single view.
Yeah.
So there's unknown, it's like a sort of bottom type or unknown.
So unknown is actually an exception in the action monad. There's an exception called stop. And stop is an exception. You can catch it with on stop, but all the default handlers will ignore stops. So, for example, the main program, if it gets a stop, it just throws it away. Or a response to a button press, then when handling that, it'll just throw that away. It's like you tried to do a thing, and it failed, but no worries. And when you try to get something that's unknown, that will generate a stop. But you can catch it if you want. Right? Yeah, anything else? Anyone?
I missed the first minute. Did you talk about how the store is implemented?
Oh yeah, it's a SQLite 3 database with 2 tables.
Okay, SQLite.
Yeah.
Okay.
SQLite.
We're in America now.
SQLite. It's a SQLite. It's only got one vowel, right? SQLite.
Did you coin the term golden typing?
Yes.
Can I use it?
Yes. I mean, yes, please do. I'm sure Stephen Dolan would be very happy. I don't know. Yeah, so I've been calling it Dolan typing. So.
Is the paper that you wrote called algebraic subtyping?
That's it. Yes, his dissertation. Yes, and if you go to Pinafore.info, I think I linked to that as well.
Oh, sorry. What language did you implement this in?
Haskell.
Oh, great.
Yeah. And right now I have a little. The Pinafore application has a sort of interactive mode as well that I've implemented, similar to GHCI, and allows you to kind of run expressions and determine the types of expressions and simplify types as well, because type simplification is a kind of a big deal.
So
exception, and then you corrected yourself to say it would be a compiler error. Is there a distinction? Or
Yes. Oh, yes. Yeah, type checking. Yeah, so it's an interpreted language, but there's a type checking step before it's run. So yeah, there's.
So you can get static value type errors, preferably with some sort of pointer to exactly what's wrong or whatnot, or actually interpreting it. Or is that
Yes. So during the type checking step, it will. If there's a type error, it'll say type error at this line in your code.
Okay. Thank you.
Did I miss you talking about putting indexes on this triple star, or is that not necessary for triple stars?
It's not necessary for the triple store. So there's a predicate, subject, object columns. Predicate and subject are the primary key.
Do you have any, what's the runtime? Is it web or something?
Oh, yeah. I could attempt to give a demonstration, but I haven't really planned on that.
I'm also curious if you have to generate a runtime system to support this language, or if it.
It's interpreted, so it just
Oh.
it just runs in.
Okay.
It's a large runtime, just called an interpreter.
Yeah, let's see if this works. Actually. So I can show you an example of what a example script looks like, if I can find it. Examples. PQRST. Yeah. So there's an example of a script. So in this part, I'm talking about sort of persons and companies or something. So here, person is a subtype of type called legal entity. And then here I can declare the set of all persons. But to do that, I can't, because Pinafore doesn't store entities per se, it stores relationships between entities. So in this case, what I have to do, if I wanted to have some notion of a particular set of persons, then I'd have to say all the persons that match a particular predicate. So let's see what happens if we can run this. Yeah. Okay, so this is just this is a window with there's a list of people. Let's see if we can create one. New person. Okay. Okay, so this created a new person with name unknown because I haven't actually specified it. Right? So there's our James. And then I put in the city. It's in Portland, wherever. Yeah, there are performance issues. That's one of the things I'll be working on next. So here now we have two views that are looking at the same entry, and then when we change one of them, it will change the other as well. So this is the sort of thing you can do with it.
Why did you find it necessary to implement the automatic updating across preferences?
It just made sense to me. But
Okay.
yeah, I mean there are There are a number of performance problems because I'm doing a lot of conversion between isomorphic types. For example, between A and list of A, unit, or rather pair of A, unit. Lots of those back and forth, which is slowing everything down. I figured out a way of fixing that, but I haven't implemented it yet. I haven't finished implementing yet. And also, it might make more sensible, rather than updating that field with every key press, maybe it should update that field after I've left that field. That might be a better.
So, sorry, we have references to the data, and the identity of the data is the hash. Is that correct?
Yeah, so if you have a piece of text, as the text type, it's just a piece of text. When it gets converted to the entity type, that then it just gets hashed, and then the entity type just wraps that UID.
My question goes towards open types and things that you might change the fields. Are those hashed as well?
No, so when you create a value of an open type, it just gives you a new UID. And that's not hashed, that's just generated randomly. And so when you create properties of that, then you can change those properties without changing the person.
It is still hashed. So references from other entities, did you clone or?
No, there isn't really a concept of cloning as such.
A single schema is not.
You don't do any database like migrations. They're not necessarily a triple store.
Right. For the most part, yeah. So I tried to make it so that you could make a lot of changes to your schema without actually touching storage. So you don't need to reload things. I mean, in some cases, if you want to do a complete refactoring, then maybe you'd want to maybe you'd want to rewrite storage somehow. But for the most part, I tried to make it robust.
Could you also generate like an HTTP API?
I haven't written that, but yes, I mean that's one direction the project could go. So I could have a web services API, but for the time being, this just works with GTK user interfaces.
So when you set a reference, does that cause a write? Or that's when the actual the action is evaluated?
Yeah, so when you create, so that thing is of type action, right? And when you execute that action, then it will execute that, setting that reference.
So where I'm going with this is like, transactional, set a bunch of things in one go to get them all written to the triple store in one shot, or so is it sort of
I hadn't really considered that. The idea is it's one user using the user interface, so you don't really need to worry about concurrency.
I suppose if you set a reference to a collection, then that's atomic, isn't it? If you have updated this collection, you set it.
Yes, probably. The code that writes to the storage is, it does use the appropriate locks. So if it does happen to be called multiple times, then only one of those writes will happen at a time.
Is the schema persisted in triple store also?
No. So the schema is what you write here in your script. This is all this stuff here, right? So here,
right.
Yeah, this is how you create the schema, right?
So if I change the name of one of my anchors, then that would make a whole new triple store.
It'll make a whole new predicate in your triple store. If you change an anchor, it'll be identified as a different predicate or different entity, or whatever that thing was. Because it's the anchors that actually identify things.
So, okay. Seems like something that might be nice to persist in database rather than type.
So this was a deliberate design decision was to separate type from data. The data gets stored, and the type is in your script.
So if you were to change one of these open types to have additional data fields,
There are no, you mean additional properties?
properties, yes.
Yeah, you can add new properties, that's not a problem.
And the ones that are already identified that you had made before, you were then to try to, deserialize one of those, get that out of your triple store. Would it have the properties and it'd be empty? It says nothing, or?
So if I were to add a new property for a person, I could just create that. I don't know. So I create like maybe like a spouse property or something. From person to maybe person. And then I give that a new anchor. Let's use a string one, it's a bit easier. Yeah. So in that case, that's just now a new property. It doesn't affect any of the other properties.
And it's just not present on any of the ones that have been persisted up till now.
Right. It's just it's a completely new thing that will, it's completely independent. You can set values of that property.
How involved are you with the triple store community? I know that there's a big web community that's pushing the triple store for linked data and such.
I'm not.
They have creative ways of querying linked data stores, making like a query language.
Right. This isn't really connected with that. Triple stores are how RDF is stored, for example, I think. But I'm not. I'm not doing anything that's connected to that directly.
Okay.
It's just a useful structure. The triple store is a really basic structure. It's extraordinarily flexible. You can throw stuff in there. There's very little structure there, so it gives me the ability to create my own kinds of structure in the language.
Do you have any concerns about the performance of this triple store? Larger data sets.
That's the least of my performance problems for the time being. In principle, I could use any. So right now, I'm using a SQLite database, but it's just two tables, right? So I could use a different database system as long as I had those two tables.
Have you looked at using something that's not SQLite?
Not for a proof of concept. It's just for this, it's been fine. It wouldn't be difficult. The Haskell bindings to databases, there's quite a lot of libraries for that.
Right.
So
I'm just curious if you wrote it in a way that's agnostic enough that it could be used with anything that's more optimized for specialized for triple stores.
Yeah, maybe. I could. Yeah, that wouldn't be hard to rewrite that backend if I wanted to.
I have one last question.
Okay.
Did I miss explanation for the name of this language?
Sorry?
Why is it called Pinafore?
Oh, it's just no one else was using the name Pinafore, so it's not particularly connected with the Gilbert and Sullivan opera.
I was going to say you can't add on languages available.
You
can keep going with the Gilbert and Sullivan.
I could. It's like a word. There are every possible word has been used for some projects. So no one's used the word Pinafore. It's a sensible work-related garment. It's